Hello everyone, my name is Arnav Jain and I am from Ramdev Baba University, and today I will be presenting a topic that lies at the heart of linear algebra and has powerful application in various scientific and technological fields: eigenvalues, eigenvectors, Hermitian and unitary matrices. We will look at what they are, how to work with them, and most importantly, why they matter. Let's start with a simple idea. Imagine you are pushing a book across a table. The direction it moves depends on the way you push it, right? In math, we often represent directions and magnitudes using vectors. Now, when we apply a matrix to a vector, we are essentially transforming it, maybe rotating it, scaling it, or flipping it. But there are some special directions, vectors, that don't change direction at all when transformed. These are called eigenvectors, and the scale by which they change is called the eigenvalue. Today, I'll walk you through what these concepts mean, how we calculate them, and why Hermitian and unitary matrices are important tools in both theory and practices. Before we dive into eigenvalues and eigenvectors, let's quickly review what a matrix does. A matrix can represent a transformation. Think of a 2D matrix rotating a shape, stretching it, or compressing it in a certain direction. For example, when we apply a matrix to a vector, the result is a new vector pointing in a different direction. But for some vectors called eigenvectors, applying the matrix doesn't change their direction, just their length. That's what makes them special. So what's happening geometrically? Let's say we apply a matrix to a vector. Usually the output is skewed or rotated, but in the case of an eigenvector, it stays on its line. It just gets longer or shorter. The factor by which it scales is the eigenvalue. For example, if a matrix stretches a vector by a factor of 3, then 3 is the eigenvalue, and the vector is the eigenvector for that transformation. This idea helps simplify complex transformation by revealing their natural directions. Now, to find the eigenvalues, we use this formula A v equals to lambda v, which can be rearranged to A minus lambda I into v equals to 0. This is a homogeneous system of equations, and for it to have a non-trivial solution, the determination must be 0. This leads us to characteristics polynomial, a polynomial whose root are the eigenvalues of the matrix. Once we find the eigenvalues, we plug, we plug them back into our equation to find the eigenvectors. Once we have lambda, the eigenvalues, we solve the equation a minus lambda I into v equals to 0 to find the eigenvector v. These vectors are linearly independent, and for a square matrix with distinct eigenvalues, we can get a complete set of eigenvectors that span the space. This allows us to understand how the matrix behaves in terms of scaling and transforming space along those key directions. Now let's take a look at Hermitian matrices. These are matrices that are equal to their own conjugate transpose. This means that the element in the ith row and the jth column is the complex conjugate of the element in the jth row and ith column. In real matrices, this simply means the matrix is symmetric. One major property of Hermitian matrices is that their eigenvalues are always real. This is incredibly useful when working with a system that must produce real-world measurable quantities. In physics, particularly in quantum physics, Hermitian matrices represent measurable quantities like energy, momentum, and position. These are called observables. Since measurement results are real numbers, Hermitian matrices are perfect for modeling them. For example, the Hamiltonian which governs how a quantum system evolves over time, is a Hermitian matrix. Another important feature is that eigenvectors of Hermitian matrices are orthogonal, meaning they meaning they form a nice clean coordinate system. Let's now shift to unitary matrices. A matrix is unitary if its conjugate transpose is also its inverse. In other words, U transpose U equals to I. This means it preserves the length of vectors and the angles between them. If you have studied orthogonal matrices in real numbers, unitary matrices are their complex counterparts. Instead of distorting a space, unitary matrices perform rotations or reflections without changing distances. That's why they are so valuable. Unitary matrices are used in quantum computing to ensure that probability is conserved during computations. Every quantum gate must be unitary because quantum states are represented as complex factor whose total probability must always equals to 1. These are also used in signal processing, like in the discrete Fourier transformation, to switch between the time and frequency domains without losing energy or information. A huge benefit of knowing eigenvalues and eigenvector is that we can perform decomposition. If a matrix A can be written as A equals to P D P inverse, where D is a diagonal matrix of eigenvalues and P contains the eigenvectors, then operations like matrix powers or exponentials become way easier. If A is Hermitian, P is unitary matrix, this decomposition is especially useful in solving systems of differential equations, performing optimization, and analyzing stability. As I mentioned earlier, quantum states evolve using unitary transformations. Hermitian operators are used to measure properties of these states. When you measure a quantum system, the result is eigenvalue of the Hermitian matrix, and the system collapses into the corresponding eigenvector or quantum state. This shows how deeply eigenvalues and matrix theory are embodied into the very fabric of how the universe works at the microscopic level. In machine learning, especially in principal component analysis or PCA, we use eigenvectors of the data's covariance matrix to reduce dimensions. This allows us to retain the most important feature of a dataset while ignoring noise and redundancy. Eigenvalues tell us how much variance is captured by each principal component, which makes the data more manageable and often improvise the perform of models. In engineering, eigenvalues are used in mechanical systems to study vibrations. Each mode of vibration corresponds to an eigenvector and its frequency is the eigenvalue. In electrical engineering, eigenvalues help us determine system stability, whether a system will respond calmly to inputs or spiral out of control. In control theory, placing eigenvalues in specific regions of the complex plane allow engineers to design stable feedback systems. Another rich area of application is signal processing. The fast Fourier transform relies on unitary matrices to convert a time domain signal into its frequency components. Because these matrices are unitary, they preserve signal energy and prevent distortion. This is critical for compression, algorithm, audio, and image analysis, and even communication systems like Wi-Fi and mobile networks. To wrap up, we have covered a lot eigenvalues and eigenvectors let us understand the fundamental directions in which a matrix acts. Hermitian matrices give us real, reliable outcomes and orthogonal directions, perfect for physics. Unitary matrices preserve structure and energy, which make them essential in quantum computing. signal processing, and more. These are not just abstract concepts, they are powerful tools used in some of the most cutting edge technology today. Thank you so much for your time and attention. I hope this presentation has given you a deeper understanding of how these matrices concepts work and why they are so important. If you have any question or would you like further clarification, I would happy to answer. Just comment down your questions below and I will answer them. Have a great day.